DNN that are widely used, along with models such as LSTM, and it can capture data continuously. And as you can see here in the picture, ANN was used in 12 studies, LSTM in 9, DNN 5, and Ensemble, which is the combination of other AI algorithms, are considered 5 times. And the picture on the right side shows 40 AI-based emission estimate studies. Is based on 40 AI-based estimation studies, or excuse me, primarily pollutants estimate for NOx, CO, carbon monoxide, carbon dioxide, and hydrocarbons. So NOx is most frequently estimated pollutant appearing in 32 studies, followed by carbon monoxide in 22 studies, and carbon dioxide 18 studies, and hydrocarbons in 17 studies. So and we established the framework to develop an emission estimation model links to the RDE experimental driving data. RDE stands for the real driving emission data, and there's usually 2 types of data used for this kind of research, which is RDE, real driving emission database, and worldwide harmonized light vehicle test process. But this study only focuses on the RDE database. So the RDE data was obtained from the National Institute of Environmental Research, which in Korea, which provides pollutant-specific emission and speed information at a microscopic time scale. It's approximately 1 second intervals. So this study uses pollutant-specific emission and speed information from RDE data as input variables for AI-based emission estimate this model. And also this data includes not only emission and speed measurements from the RDE test itself, it also includes various additional parameters such as driving mode, temperature, and humidity. So yeah, and this data is collected under various driving conditions in accordance with the RDE regulations, which require driving duration of 90 to 120 minutes in either cold or hot conditions. So these RDE data records pollutant emissions, which I mentioned, CO, CO2, NOx, and THC for each driving mode, including cold transient, cold satellites, and hot transient. It's the 3 major phases of driving condition to test this data. And also the driving tests were conducted under real-world conditions, which means it includes urban, suburban, and highway driving and emission variations were observed based on fuel type, vehicle model, and information. So this is the pre-processing which we've done for this. We actually acquired a vehicle specification data. It was compiled using automobile manufacturer websites in Korea, like Hyundai and Kia, and related resources. And this data is matched with the RDE data from the National Institute of Environmental Research. And the key target variables in the AI-based emission model include RDE pollutants, 4 pollutants, which I mentioned before, and along with these emission amounts, it includes the speed information for different starting conditions. Okay, to align with the emission estimation units, converted this real-time emission data from RDE to gram per second and gram per kilometer units for this AI-based emission model. So one thing we've done to process the emission data in gram per second units. The emission amounts were actually divided by time. So additionally, real-time speed information was used to calculate real-time travel distances, which allows emissions to convert into gram per kilometers, also units also by dividing the total emissions by the corresponding travel distance. And the scatter plot, as you see here in the left side, was conducted to investigate the correlation between instantaneous vehicle speed and emissions. Speed has been identified as a key influencing factor in vehicle emissions in previous studies. So the results, the analysis revealed, the difficulties in identifying a consistent correlation between instantaneous instantaneous speed and emissions. So particularly in low speed and high speed ranges, in the red box, which is marked in the red box, has no clear pattern between speed fluctuations and emission variations, which leads to suspicions of outliers in certain data points. Since outliers cannot be determined solely based on scatter plots, and emissions are influenced by complex relationships involving vehicle specification and external factors, it was concluded that applying advanced outlier detection algorithms in AI models incorporating multiple variables would be more effective. So we also defined a database with multiple AI algorithms. Here the goal was to apply AI algorithms, which is suitable for different driving conditions and emission characteristics. Which is to construct an emission prediction model by leveraging the strengths and unique features of each algorithm to enhance prediction accuracy. So each prediction models were built using various algorithms like random forest or ANN-MLP, Vector Regression, and something like that. We also applied a moving average, which is because the raw data of RDE is collected at microscopic time, intervals of approximately 1 second. So during the initial development of validation for this AI model, we found that learning the emission patterns associated with speed variation as such, fine time intervals was a little bit challenging. So, and the RD data was aggregated. So the RD data was aggregated into various time intervals ranging 1 second to 600 seconds to pre-process per second emissions and per distance emissions, which were then used for AI machine learning model development. So these per second emissions were calculated by dividing the accumulated pollutant emissions measured over a specific time interval by the corresponding driving time. And this approach was implemented to reflect how emissions fluctuate over timing analysis. Also, the per distance emissions were calculated by dividing the total accumulated pollutant emissions over a given period by the corresponding driving distance. So this approach was used to account for variations in pollutants concentration based on driving distance and conditions. And we also tried to find the optimal hyperparameters. So as you have heard about this AI, sort of AI machine learning, we need to optimize the performance of AI machine learning models. Various hyperparameters such as learning rate, number of hidden layers, and optimization techniques were adjusted as follows. And also we use the model for scikit learners, research and random search, to explain, briefly to explain about the research method and random search method. The research methods allows you to make a clear analysis of how each parameter affects the model. However, as the number of combination increases, the computational cost grows exponentially. And the search is limited to predefined parameter range. Besides that, random search. Random samples specify number of parameter combinations, and it has a high probability of finding optimal parameters with manual computation. However, since it does not explore all possible combinations, there is a possibility of missing the best parameters. In this research, we found that the grid research is better than the random search for these AI models. And these are the results of our AI model which we built. And here you can see the difference performance with the graph per second and graph per kilometers by each AI models. The R-square at the right side ranges between 0 and 1, which values close. If the value closer to 1 indicates that the model explains data well. So the darkest color shows that it fits to the R-square. So this analysis result shows that as the size of the moving average increases, the model's goodness of fit, which is also called R-square, generally improves. So what this result suggests to you? Emission fluctuations at microscopic timescale are significant. That indicates that the constructed explanatory variables may not be sufficiently suitable for the predicting emissions at such a fine temporal resolution. So these findings imply that it is difficult to fully explain the noise inherent in the RD data at a microscopic level. So our next goal for this research is to optimize emission prediction at the microscopic level, which is also called tier 3, minimizing this size of moving average appears to be up here, and also we validated this AI model results by simulation using a model called VC. So we first set a corridors, the pathways which the RD test was activated. So we defined, so we tried to display the network here. And we converted it into a graph. We're combining this AI-based emission analysis and missing data. So as you can see, as the time flows, you can see the difference of changing emission rate between type of vehicles. So the conclusion. The analysis indicates a general increase in variability as the moving average window size grows, as you see by the results. So this suggests that the emission data aggregated at a very fine, the micro level, time scale, and with a significant variability. But these variables may not be sufficiently suited for prediction at such a micro level resolution. So, since the current sample size is not large enough, there is a clear need to collect additional RD data to facilitate the development of more advanced AI machine learning models. explaining such emissions variability at 1 second micro level. We expect to explore transfer learning and hybrid modeling approaches via integration with external models such as autonomy and loop in viable option for viable option and forward. This is the schema of our future research. And these are the papers and literatures we research. And thank you for listening to my